Introduction to 464XLAT. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. Today we're diving into 464XLAT, which stands for Combination of Stateful and Stateless Translation. This technology represents a critical solution in the ongoing transition from IPv4 to IPv6 networks. As Internet service providers and mobile carriers increasingly deploy IPv6-only networks to conserve the rapidly depleting IPv4 address space, they face a significant challenge. Millions of applications and services still rely exclusively on IPv4 connectivity. This creates a fundamental problem where IPv6-only devices cannot communicate with IPv4-only servers. 464XLAT solves this incompatibility by implementing a two-stage translation mechanism. The first stage involves Customer-side Translator, abbreviated as CLAT, which runs on the end-user device itself. This component translates IPv4 packets generated by legacy applications into IPv6 packets that can traverse the provider's IPv6-only network infrastructure. The second stage involves Provider-side Translator, abbreviated as PLAT, which operates in the service provider's network core. The PLAT receives these specially formatted IPv6 packets and translates them back into standard IPv4 packets before forwarding them to IPv4 destinations on the public Internet. The IPv4 exhaustion problem. To understand why 464XLAT exists, we need to examine the IPv4 address exhaustion crisis that drove its development. IPv4 uses 32-bit addresses, providing approximately 4.3 billion unique addresses. When IPv4 was designed in the 1980s, this seemed like an enormous address space that would last indefinitely. However, the explosive growth of the Internet, proliferation of connected devices, and inefficient early allocation practices led to rapid consumption of available addresses. The regional Internet registries, known as RIRs, began running out of available IPv4 addresses in the early 2010s. IANA, the Internet Assigned Numbers Authority, exhausted its central pool of IPv4 addresses in February 2011. Subsequently, APNIC for Asia Pacific exhausted its pool in April 2011. RIPENCC for Europe in September 2012. LACNIC for Latin America in June 2014. And ARIN for North America in September 2015. AFRINIC for Africa is expected to exhaust soon. This depletion forced organizations to implement various conservation techniques, including network address translation with carrier-grade NAT, address trading markets, and aggressive reclamation of unused address blocks. Mobile network operators faced particularly acute challenges because smartphones, tablets, and IoT devices drove exponential growth in connected devices. Assigning public IPv4 addresses to every mobile device became economically and technically infeasible. Carrier-grade NAT introduced significant operational complexity, connection tracking limitations, degraded application performance, and difficulties with protocols requiring end-to-end connectivity. IPv6 adoption became not just desirable but essential for sustainable network growth. However, simply deploying IPv6 was not sufficient because vast portions of Internet content and services remained IPv4 only, necessitating transition mechanisms like 464XLAT. IPv6 deployment challenges. While IPv6 provides a virtually unlimited address space with its 128-bit addressing scheme, its deployment has faced numerous obstacles that delayed widespread adoption for decades. The primary challenge is the lack of backward compatibility between IPv4 and IPv6 protocols. These are fundamentally different protocols with different packet structures, header formats, addressing schemes, and control mechanisms. An IPv6-only device cannot directly communicate with an IPv4-only device without some form of intermediary translation or tunneling mechanism. The chicken and egg problem of IPv6 adoption created significant inertia. Content providers were reluctant to invest in IPv6 infrastructure when few users had IPv6 connectivity, while ISPs hesitated to deploy IPv6 when little content was available over IPv6. This created a circular dependency that slowed deployment. Additionally, many enterprise networks, data centers, and service providers had massive investments in IPv4 infrastructure, including routers, switches, firewalls, load balancers, and management systems that would require expensive upgrades or replacements to support IPv6. Application compatibility presented another major hurdle. Many legacy applications, particularly in embedded systems, industrial control systems, and older enterprise software, were hard-coded to use IPv4 addressing. These applications would require significant redevelopment or replacement to support IPv6. Network operators also faced staff training challenges since IPv6 requires different operational procedures, troubleshooting techniques, and security considerations compared to IPv4. The complexity of running dual-stack networks during transition periods increased operational overhead and potential configuration errors. Translation versus tunneling approaches. Network engineers developed two fundamental approaches for enabling communication between IPv4 and IPv6 networks: tunneling and translation. Understanding the differences between these approaches is crucial for appreciating why 464X-LAT uses its specific architecture, combining both stateless and stateful translation mechanisms. Tunneling encapsulates IPv4 packets inside IPv6 packets for transport across IPv6 networks, or vice versa. Common tunneling protocols include 6to4, which automatically tunnels IPv6 packets over IPv4 infrastructure; Teredo, which allows IPv6 connectivity through IPv4 NAT devices; and ISATAP for intra-site automatic tunnel addressing. Tunneling preserves the original packet structure and addressing information, making it relatively simple to implement. However, tunneling adds overhead through additional headers, increases packet size, potentially causing fragmentation issues, and can complicate firewall rules and security policies. Tunneling also requires both endpoints to support the tunneling protocol, limiting its applicability for general Internet connectivity. Translation mechanisms convert packets between IPv4 and IPv6 formats, modifying headers and addresses during the conversion process. NAT64 performs stateful translation between IPv6 clients and IPv4 servers, while DNS64 provides synthesized IPv6 addresses for IPv4-only destinations. Translation approaches offer several advantages. They do not increase packet size with additional headers, they are transparent to applications that see native protocol packets, and they can support asymmetric scenarios where one side only implements one protocol version. However, translation faces challenges. For example, address mapping complexity, protocol-specific translation requirements for embedded addresses in application protocols like FTP, and potential issues with applications performing integrity checks on packet contents. 464X-LAT Architecture Overview. 464X-LAT combines stateless and stateful translation in a unique architecture specifically designed for provider-managed IPv6-only networks that need to support IPv4 applications. The 464 designation comes from the translation sequence IPv4 to IPv6 to IPv4, representing the complete path a packet takes from source to destination. The XLAT abbreviation stands for translation, highlighting the core mechanism used throughout the system. The architecture consists of two primary translation components working in tandem. The customer-side translator, or CLAT, operates on the end-user device such as a smartphone, tablet, or customer premises equipment. The CLAT implements stateless translation using protocols defined in RFC 6145, converting IPv4 packets from applications into IPv6 packets suitable for transport across the provider's IPv6-only access network. This translation is stateless, meaning the CLAT does not maintain connection state tables, making it lightweight and suitable for resource-constrained mobile devices. The Provider-side Translator, or PLAT, operates in the service provider's network core, typically at the network edge where the IPv6 access network connects to the IPv4 Internet. The PLAT implements stateful translation using NAT64 protocols defined in RFC 6146, maintaining connection state tables to track active sessions and manage address port translation. The PLAT translates the IPv6 packets received from CLAT back into standard IPv4 packets before forwarding them to IPv4 destinations. By combining stateless CLAT with stateful PLAT, 464XLAT achieves efficient resource utilization on end devices while centralizing complex state management in provider network infrastructure where resources are more abundant. CLAT component details. The customer-side translator represents the client-side implementation of 464XLAT, typically integrated into operating systems of mobile devices or implemented in customer premises equipment. Modern smartphone operating systems, including Android, iOS, and various Linux-based systems, include native CLAT functionality that activates automatically when the device detects it is connected to an IPv6-only network that supports 464XLAT. CLAT operation begins with the device obtaining an IPv6 address through standard IPv6 mechanisms, for example, SLAAC, which stands for Stateless Address Autoconfiguration, or DHCPv6. The device also discovers the PLAT prefix, typically the well-known prefix 64:FF9B:/96, defined in RFC 6052, though network operators can configure custom prefixes. When an application generates an IPv4 packet destined for an IPv4 address, the packet first passes through the device's networking stack where CLAT intercepts it before it reaches the physical network interface. The CLAT performs stateless translation by creating a virtual IPv4 interface, usually with an address from the 192.0.0.0/29 range reserved for this purpose. The CLAT translates the source IPv4 address to an IPv6 address by combining the device's actual IPv6 prefix with the IPv4 address bits embedded according to RFC 6052 formatting rules. Similarly, the destination IPv4 address gets translated to an IPv6 address using the PLAT prefix plus the embedded IPv4 destination. The resulting IPv6 packet contains all the original information from the IPv4 packet but in a format that can traverse the provider's IPv6-only network. Because this translation is algorithmic and stateless, the CLAT requires minimal memory and processing resources, making it suitable for mobile devices with limited battery capacity and computational power. PLAT component details. The Provider-side Translator operates as a stateful NAT64 gateway in the service provider's network infrastructure, typically deployed at strategic points where the IPv6 access network connects to the IPv4 Internet. Mobile network operators usually deploy PLAT functions in their core network or at regional peering points to minimize latency and maximize efficiency. The PLAT must be dimensioned to handle potentially millions of concurrent connections from all subscribers using 464XLAT across the provider's network. When the PLAT receives an IPv6 packet from a CLAT, it first extracts the embedded IPv4 destination address from the IPv6 destination address, using the configured prefix mapping. The PLAT then performs stateful NAT64 translation, which involves several critical operations. First, It allocates an IPv4 source address and port from its pool of public IPv4 addresses. This creates a binding entry in its connection state table that maps the internal IPv6 source address and port to the external IPv4 address and port. This state table allows the PLAT to correctly route return traffic back to the original sender. The PLAT reconstructs the IPv4 packet header using the extracted destination address and the allocated source address and port. It recalculates checksums for both the IP header and transport layer protocols, like TCP or UDP, ensuring packet integrity. The PLAT also handles protocol-specific considerations, such as ICMP message translation, fragment handling, and management of embedded IP addresses in application layer protocols, like FTP or SI pages as a stateful device. The PLAT maintains connection tracking tables, implements timeout mechanisms for idle connections, and must handle session persistence for protocols requiring consistent addressing across multiple packets. High availability deployments typically use redundant PLAT instances with state synchronization to prevent service disruption during failures. Packet flow analysis. Understanding the complete packet flow through a 464x LAT system reveals how the various components work together to enable IPv4 application connectivity over IPv6-only infrastructure. Let's trace a typical HTTP request from a smartphone app to an IPv4-only web server to see the translation process in action at each stage of the journey. The flow begins when an application on an IPv6-only smartphone attempts to connect to an IPv4 web server at address 203.0.113.10 on port 80. The application, unaware of the underlying network architecture, generates a standard IPv4 packet with source address 192.0.0.1, which is the virtual IPv4 address assigned by CLAT, and destination address 203.0.113.10. The device's networking stack routes this packet to the CLAT function, which intercepts it before transmission. The CLAT performs stateless translation, converting the packet to IPv6 format. It translates the source address 192.0.0.1 to an IPv6 address by combining the device's actual IPv6 prefix, let's say 2001:DB8:1:2:/64, with the embedded IPv4 address according to RFC 6052 rules, resulting in something like 2001:DB8:1:2:192.0.0.1. The destination address 203.0.113.10 gets translated using the PLAT prefix 64:FF9B::/96, becoming 64:FF9B::203.0.113.10. The resulting IPv6 packet travels across the provider's IPv6-only network to the PLAT. Upon receiving the IPv6 packet, the PLAT extracts the embedded IPv4 destination 203.0.113.10 and performs stateful NAT64 translation. It allocates a public IPv4 address from its pool, say 198.51.100.5, and selects an available source port like 52000, creating a state table entry mapping this to the original IPv6 source. The PLAT creates a new IPv4 packet with source 198.51.100.552.000 and destination 203.0.113.1080. Then forwards it to the IPv4 Internet. Return packets follow the reverse path, arriving at the PLAT as IPv4, getting translated to IPv6 using the state table mapping, traversing the IPv6 network, and finally being translated back to IPv4 by the CLAT before delivery to the application. Address mapping mechanisms. Address mapping in 464-XLAT follows specific rules defined in RFC 6052 for embedding IPv4 IPs within IPv6 IPs. These mapping rules ensure consistent and reversible translation while maintaining uniqueness and proper routing through the IPv6 network. Understanding these mapping mechanisms is essential for network operators implementing and troubleshooting 464-XLAT deployments. The most commonly used approach employs the well-known prefix 64:FF9B:/96, which IANA specifically allocated for IPv4 to IPv6 translation. This prefix provides a standardized way to represent any IPv4 address as an IPv6 address. The mapping works by taking the 32 bits of the IPv4 address and placing them in the last 32 bits of the IPv6 address after the 96-bit prefix. Network operators can also configure network-specific prefixes instead of using the well-known prefix, allowing them to use their own IPv6 address space for translation. This approach, defined in RFC 6052, supports various prefix lengths including /32, /40, /48, /56, /64, and /96. When using shorter prefixes, the IPv4 bits are embedded at different positions within the IPv6 address according to specific encoding rules. For example, with a /64 prefix like 2001:DB8:64:/64, the IPv4 address bits occupy positions 64 through 95 of the resulting IPv6 address. Using organization-specific prefixes offers several advantages. It allows translation to work within the organization's own address space, enables more flexible routing policies, and can improve troubleshooting by making translated addresses easily identifiable as belonging to the organization's network. However, it requires additional configuration on CLAT devices to discover and use the correct prefix, typically accomplished through DHCPv6 options or router advertisement extensions. DNS-6.4 integration. DNS-6.4 serves as a critical companion technology to 464-XLAT, providing the DNS infrastructure necessary for IPv6-only clients to discover and connect to IPv4-only services. While 464-XLAT handles packet translation, DNS-6.4 ensures that applications receive usable addresses through the domain name resolution process. Understanding how DNS-6.4 integrates with 464-XLAT is essential for deploying fully functional IPv6-only networks. DNS-64 operates as a specialized DNS server that intercepts DNS queries from IPv6-only clients and synthesizes IPv6 addresses for IPv4-only destinations. When an application on an IPv6-only device performs a DNS lookup for a domain name, it first queries for AAA records, which contain IPv6 addresses. If the DNS-64 server finds native AAA records in the authoritative DNS, it returns those addresses directly, allowing the client to use native IPv6 connectivity without any translation. This preserves optimal performance for IPv6-enabled services. However, when the query domain has only a records containing IPv4 addresses and no AAA records, DNS-64 performs address synthesis. It retrieves the IPv4 address from the A record and combines it with the configured translation prefix, typically the same prefix used by the PLAT component, to create a synthetic AAA record. For example, if the domain resolves to IPv4 address 93.184.216.34 and the PLAT uses prefix 64:FF9B:/96, DNS-64 synthesizes the IPv6 address 64:FF9B:93.184.216.34 and returns this in an AAA record to the client. The client application, receiving what appears to be a normal IPv6 address, initiates communication using this address. The packets then flow through the CLAT and PLAT as previously described. DNS64 configuration requires coordination with the PLAT deployment to ensure that prefix usage is consistent. Operators must configure DNS64 servers with the same translation prefix used by PLAT devices. Otherwise, address synthesis will not align with translation policies, and connections will fail. DNS64 also implements sophisticated logic to avoid synthesizing addresses for certain IPv4 ranges, such as private addresses or addresses that should not be globally reachable. Many implementations support whitelisting and blacklisting domains to control which queries receive synthesized responses. This allows operators to enforce policies about which services can be accessed through translation, versus requiring native IPv6 connectivity. CLAT discovery mechanisms. For 464XLAT to function properly, the CLAT component on the client device must discover several critical parameters before it can begin translation operations. This discovery process ensures the CLAT has all necessary information to correctly translate packets and route them through the provider's IPv6 network to the appropriate PLAT. The discovery mechanisms are standardized to enable interoperability across different device manufacturers and network operators. The primary discovery task involves determining the PLAT prefix, which tells the CLAT how to construct destination IPv6 addresses for IPv4 destinations. Multiple discovery methods exist, providing fallback options if preferred methods fail. The most common approach uses DNS-based discovery through special queries. The CLAT performs a DNS query for the domain IPv4-Only.ARPA, which is specifically designed for 464XLAT discovery. If the network has DNS64 deployed, this query will return a synthesized AAA record containing the PLAT prefix. The CLAT extracts the prefix from this response and uses it for subsequent translations. Alternative discovery methods include DHCPv6 options, where the PLAT prefix can be provided through option 64 in DHCPv6 responses, allowing centralized configuration management. Router advertisement extensions also support prefix distribution through specific option types defined in RFC 7225. Some implementations support manual configuration, allowing network administrators or users to explicitly specify the PLAT prefix in device settings. This is useful for troubleshooting or non-standard deployments. The CLAT also needs to determine whether it is connected to an IPv6-only network that requires 464XLAT. It accomplishes this by attempting to reach known IPv4-only destinations and detecting translation behavior, or by checking for IPv4 address assignment failure combined with successful IPv6 configuration. Protocol-specific translations. While basic IPv4 to IPv6 translation handles most traffic, certain protocols require special handling due to embedded IP addresses, protocol-specific behaviors, or checksum calculations that span multiple layers. Understanding these protocol-specific considerations is crucial for implementing a fully functional 464XLAT deployment that supports the wide variety of applications users expect to work transparently. ICMP presents unique challenges because it serves both for error reporting and diagnostic functions, such as ping and traceroute. The CLAT must translate ICMP messages between ICMPv4 and ICMPv6 formats, which have different message types and codes. For example, ICMPv4 echo request type 8 becomes ICMPv6 echo request type 128, while maintaining the same basic functionality. Error messages require special handling because they include portions of the original packet that triggered the error. These may contain embedded addresses that also need translation. The CLAT must examine these embedded packets and translate their headers recursively to maintain consistency. Fragmentation handling differs significantly between IPv4 and IPv6. IPv4 allows intermediate routers to fragment packets if they exceed link MTU, while IPv6 requires source nodes to perform path MTU discovery and handle fragmentation themselves. When translating IPv4 fragments to IPv6, the CLAT must reassemble fragments, determine appropriate IPv6 packet size, and potentially refragment if needed according to IPv6 rules. The PLAT faces similar challenges in reverse when translating from IPv6 to IPv4. Application layer gateways, abbreviated as ALGs, are required for protocols that embed IP addresses in payload data. FTP is a classic example where port and PASV commands contain ASCII-encoded IP addresses and ports that must be translated and modified within the application payload. SIP, used for VoIP, includes IP addresses in SDP session descriptions that require translation. The PLAT typically implements these ALGs since it has more resources than client-side CLAT implementations. Stateful versus stateless operation. The 464XLAT architecture cleverly combines stateless translation on the client side with stateful translation on the provider side, achieving an optimal balance between resource efficiency, scalability, and functionality. Understanding the differences between stateful and stateless operation clarifies why this hybrid approach was chosen and how it benefits both end users and network operators. Stateless translation, as implemented by CLAT, performs algorithmic conversion between IPv4 and IPv6 addresses without maintaining any connection state or session tables. Each packet is translated independently, based purely on the information in that packet's headers and predefined translation rules. The CLAT uses deterministic address mapping, where source IPv4 addresses from the local device always map to the same IPv6 addresses using the device's IPv6 prefix. Destination IPv4 addresses consistently map to IPv6 addresses using the PLAT prefix. This stateless approach offers several advantages. Minimal memory footprint since no state tables are needed. Simple implementation suitable for resource-constrained mobile devices. No session timeout management required. And resilience to crashes or restarts, since no state needs recovery. Stateful translation, as implemented by PLAT, maintains connection state tables, tracking active sessions. When the PLAT receives a new connection, it allocates an IPv4 source address and port from its pool. It then creates a binding entry, mapping the internal IPv6 source to the external IPv4 source, and stores this binding in a connection state table. Subsequent packets belonging to the same connection use this existing binding to maintain address consistency. The stateful approach enables critical functionality that stateless translation cannot provide. This includes port multiplexing, where multiple internal hosts share a single external IPv4 address through different port numbers. Connection tracking, which allows proper handling of bidirectional communication. Session persistence, ensuring packets in both directions of a conversation receive consistent address translation. And protocol-specific ALG functionality, which may require understanding connection state. The hybrid 464XLAT model leverages the strengths of both approaches. CLAT's stateless operation keeps client devices simple and efficient. PLAT's stateful operation, conversely, provides the sophisticated functionality needed for IPv4 address sharing and protocol support. This division of responsibilities allows mobile devices to operate with minimal overhead. It also centralizes complex state management in provider infrastructure, where computational resources, memory, and power are abundant. Mobile network deployment. Mobile network operators were among the earliest and most enthusiastic adopters of 464XLAT technology due to the acute IPv4 address shortage they faced with smartphone proliferation. Understanding how mobile carriers deploy 464x-LAT reveals the practical implementation considerations and architectural decisions involved in large-scale production deployments. Mobile operators typically deploy PLAT functions in their Packet Data Network Gateway, abbreviated as PGW or PDNGW in LTE networks, or in the user plane function, abbreviated as UPF in 5G networks. These gateway elements already perform NAT and address translation functions for traditional IPv4 connectivity, making them logical locations for PLAT implementation. High-capacity PLAT instances must handle millions of concurrent mobile subscribers, each potentially maintaining dozens of simultaneous connections across various applications. Operators deploy multiple PLAT instances for redundancy and load distribution, often using anycast routing to direct traffic to the nearest available instance. The radio access network and core network operate purely on IP version 6, with no IP version 4 addressing in the access infrastructure. When a mobile device attaches to the network, it receives only IP version 6 addressing through standard 3GPP procedures. The device performs IP version 6 stateless address autoconfiguration or receives IP version 6 addresses through DHCP version 6, depending on operator configuration. Once connected, the device's operating system detects the IP version 6 only environment and automatically activates its CLAT functionality. Android has included native CLAT support since version 4.3, iOS since version 9, and most modern mobile platforms include this capability. Operators configure DNS64 servers in their network to provide synthesized AAA records for IPv4-only destinations. These DNS64 servers are typically specified in the IPv6 router advertisement messages sent to mobile devices during network attachment. The DNS64 configuration uses the same PLAT prefix as the NAT64 gateways to ensure consistency. Monitoring and troubleshooting tools track CLAT activation rates across the device fleet, PLAT connection counts and resource utilization, DNS64 query patterns and synthesis rates, and application compatibility issues that may arise. Operators often maintain application compatibility databases documenting which apps work properly with 464x-LAT and which may require special handling or fallback to legacy IPv4 connectivity. Performance considerations. While 464x-LAT enables critical functionality by allowing IPv4 applications to work over IPv6-only networks, the translation process introduces various performance considerations that network operators and application developers should understand. These performance factors influence user experience, network efficiency, and operational costs. Translation overhead occurs at multiple points in the packet path. The CLAT on the client device must intercept every IPv4 packet from applications, translate headers, recalculate checksums, and reinject packets into the network stack as IPv6. While this overhead is minimal on modern mobile processors, it does consume CPU cycles and battery power. The impact increases with high packet rates from applications generating significant traffic. The PLAT faces more substantial processing demands since it handles aggregate traffic from thousands or millions of subscribers simultaneously. Each packet requires state table lookup or creation, header translation, checksum recalculation, and potentially ALG processing for certain protocols. Latency implications arise from the additional processing and the network path through translation gateways. CLAT translation adds microseconds of processing delay on the client device, typically negligible compared to network propagation times. However, packets must traverse the network to reach the PLAT before continuing to their final destination, potentially adding tens of milliseconds depending on PLAT placement. Optimal PLAT placement near network edges or major peering points minimizes this additional latency. Some operators deploy distributed PLAT instances geographically to keep translation close to users. Throughput and scalability depend on PLAT dimensioning and architecture. High-end PLAT implementations can handle hundreds of gigabits per second of traffic, but this requires substantial computational resources for connection tracking, table management, and packet processing. State table size grows with the number of active connections, potentially reaching hundreds of millions of entries in large carrier deployments. Memory bandwidth for state table access can become a bottleneck before CPU processing capacity. Modern implementations use optimized data structures, multi-core parallelization, and hardware acceleration to achieve necessary throughput. Session timeout values represent a critical tuning parameter. Shorter timeouts reduce state table size but may prematurely close legitimate idle connections, while longer timeouts increase resource consumption but improve application compatibility. Security implications. Translation mechanisms like 464XLAT introduce various security considerations that differ from traditional IPv4-only or IPv6-only networking. Understanding these security implications allows operators to design secure deployments and enables security teams to properly monitor and defend networks using translation technologies. The PLAT's stateful NAT functionality provides inherent security benefits similar to traditional IPv4 NAT. Inbound connection blocking occurs automatically since the PLAT only maintains state for outbound initiated connections. Unsolicited inbound packets from the IPv4 Internet cannot reach client devices unless explicit port forwarding rules are configured. This provides a default deny posture for inbound traffic, offering some protection against scanning and exploitation attempts from the Internet. However, operators should not rely solely on this for security since it's a side effect of address translation rather than a designed security control. PLAT translation provides address obscurity, meaning external observers cannot directly identify individual devices behind the translation boundary. Multiple devices share the same external IPv4 address, complicating attribution of traffic to specific users. While this provides some privacy benefit, it also complicates incident response and abuse handling, since operators must correlate timestamps with connection state logs to identify which subscriber generated specific traffic. Logging requirements for law enforcement and abuse response necessitate detailed connection state logging, including source IPv6 address, allocated IPv4 address and port, destination address and port, timestamp, and protocol information. Translation presents attack surface considerations that security teams must address. PLAT devices become critical infrastructure components whose compromise could affect all subscriber traffic. Distributed denial of service attacks targeting PLAT instances could disrupt connectivity for millions of users. Resource exhaustion attacks attempting to fill connection state tables with bogus sessions require rate limiting and connection tracking limits per subscriber. Protocol exploits in ALG implementations could potentially allow attackers to manipulate translation behavior. Security hardening of PLAT platforms includes regular software updates, strict access controls, network segmentation isolating PLAT management interfaces, comprehensive logging and monitoring, and redundant deployment with failover capabilities. Deep packet inspection and security monitoring become more complex when traffic flows through translation since traditional IPv4-based security tools may not properly understand the IPv6 transport or the translated addressing. Troubleshooting and diagnostics. Troubleshooting 464XLAT connectivity issues requires understanding the complete translation path and having appropriate diagnostic tools at each stage. Network operators and support teams need systematic approaches to identify whether problems originate in CLAT operation, network transport, PLAT translation, or application-specific issues. Client-side diagnostics begin by verifying CLAT is active and operating correctly. On Android devices, developers can check the network interface list for a CLAT4 interface, which indicates active CLAT translation. The interface configuration shows the virtual IPv4 address assigned, typically from the 192.0.0.0/29 range. Examining routing tables reveals routes directing IPv4 traffic through the CLAT interface. Testing basic connectivity involves pinging known IPv4 addresses to verify translation is occurring. Examining packets with network capture tools shows the translation in action. Outbound packets leave as IPv6 with embedded IPv4 addresses, while applications receive translated IPv4 responses. DNS64 verification confirms proper address synthesis. Performing DNS queries for known IPv4-only domains should return synthesized AAA records containing the PLAT prefix. If DNS64 isn't working, queries return only records, preventing CLAT from knowing which IPv6 addresses to use for translation. Tools like DIG or NSLOOKUP can query specific DNS64 servers to test their synthesis behavior. Checking that DNS64 uses the correct PLAT prefix matching the actual PLAT configuration prevents addressing mismatches. PLAT troubleshooting focuses on translation gateway operation and state management. Monitoring connection state table utilization reveals whether tables are approaching capacity limits that could cause new connection failures. Examining state table entries for specific flows confirms proper address allocation and binding creation. PLAT logs should record connection establishment and teardown events, ALG activations, and any translation errors encountered. Performance monitoring tracks packet processing rates, CPU utilization, memory consumption, and any packet drops or errors. Testing from behind the PLAT to various IPv4 destinations verifies end-to-end connectivity through the complete translation path. Protocol-specific testing with tools like curl for HTTP, Telnet for TCP, and traceroute for path analysis helps isolate issues to specific protocols or destinations. Alternative transition mechanisms. While 464XLAT addresses the specific use case of IPv4 applications on IPv6-only networks, it exists within a broader ecosystem of IPv4/IPv6 transition mechanisms. Understanding these alternatives and their use cases helps network architects select appropriate technologies for their specific requirements. Dual stack remains the simplest conceptual approach where networks and devices support both IPv4 and IPv6 simultaneously. Each host obtains both IPv4 and IPv6 addresses, and applications can use either protocol as appropriate. Dual stack provides excellent compatibility since devices can communicate using native protocols without translation. However, it doesn't solve the IPv4 address exhaustion problem, as every device still requires an IPv4 address. In mobile networks with millions of subscribers, dual stack deployment requires massive IPv4 address pools that simply aren't available. Dual stack also doubles the network complexity with two parallel protocol stacks requiring configuration, routing, security policies, and monitoring. NAT64 without CLAT represents standalone stateful translation between IPv6-only clients and IPv4 servers. DNS64 synthesizes AAA records, and clients connect using IPv6, with translation occurring only at the network edge. This works well for IPv6 native applications, but fails for applications that use literal IPv4 addresses or perform IPv4 connectivity checks. Many legacy applications fall into this category, making standalone NAT64 insufficient for mobile operator networks where application compatibility is paramount. 464XLAT extends NAT64 by adding the CLAT component specifically to support these problematic applications. Dual Stack Lite, abbreviated as DS-Lite, provides IPv4 connectivity over IPv6 infrastructure using tunneling instead of translation. Customer equipment receives IPv6 connectivity plus a special IPv4 address from the private range that is tunneled through IPv6 to a carrier-grade NAT in the provider network. This maintains better IP version 4 compatibility than translation approaches since actual IP version 4 packets traverse the network, only encapsulated in IP version 6. However, tunneling adds overhead and complexity compared to 464XLAT's translation approach. MAPE and MAPT, standing for mapping of address and port with encapsulation and translation respectively, represent more recent alternatives that attempt to minimize stateful infrastructure by using algorithmic address sharing schemes. These can be more efficient but require more complex client-side implementations. Standards and RFCs. 464XLAT is defined through a collection of IETF standards documents that specify the architecture, protocols, address formats, and operational procedures. Understanding these foundational RFCs provides authoritative reference material for implementation and deployment. RFC 6146 defines the stateful NAT64 protocol that forms the basis of PLAT operation. This specification describes the translation algorithms for converting between IPv6 and IPv4 packet headers, the connection state management procedures, address pool management, and handling of various protocols including TCP, UDP, and ICMP. It specifies how to handle fragmentation, perform checksum recalculation, and manage connection timeouts. RFC 6146 provides the detailed algorithmic specifications that PLAT implementers must follow to ensure interoperability and correct behavior. RFC 6145 specifies IP/ICMP translation algorithms for stateless translation, as used by CLAT. While the overall NAT64 framework is stateful, the actual packet header translation algorithms can be performed statelessly. RFC 6145 describes the specific field mappings between IPv4 and IPv6 headers, ICMP message type translations, and handling of various IP options and extension headers. CLAT implementations rely heavily on these algorithmic specifications since they perform translation without maintaining state. RFC 6052 defines the IPv6 addressing format for embedding IPv4 addresses within IPv6 addresses. This critical specification establishes the well-known prefix 64:FF9B:/96 and describes how to embed 32-bit IPv4 addresses in various positions within the 128-bit IPv6 address space depending on prefix length. It ensures consistent address mapping across different implementations and deployments. RFC 6877 specifically defines the 464XLAT architecture, describing how CLAT and PLAT components work together, the discovery mechanisms for PLAT prefix, and operational considerations for deployment. RFC 7050 describes discovery of the IPv6 prefix used for IPv6 address synthesis, defining the IPv4-Only .ARPA domain used for PLAT prefix discovery. RFC 7225 specifies extensions to IPv6 router advertisement for distributing 464XLAT configuration information. These standards collectively provide the complete specification foundation for interoperable 464XLAT implementations across different vendors and platforms. Future of 464XLAT. As IPv6 deployment continues to expand globally, the role and relevance of 464XLAT will evolve. Understanding the technology's future trajectory helps organizations plan long-term network architectures and transition strategies. Near-term growth will likely continue as more mobile operators deploy IPv6-only access networks. Emerging markets building new mobile infrastructure increasingly choose IPv6-only designs from the start rather than deploying legacy IPv4 infrastructure. 5G network deployments favor IPv6-only core networks, making 464XLAT an essential component for backward compatibility with IPv4 services and applications. IoT device proliferation drives demand for IPv6 addressing, with billions of connected sensors, meters, and embedded devices requiring unique addresses that only IPv6 can provide at scale. Many IoT devices also need occasional connectivity to IPv4 backend systems, making translation mechanisms necessary. Long-term decline seems inevitable as IPv4 usage gradually diminishes. Major content providers including Google, Facebook, Cloudflare, and many others now serve the majority of their traffic over IPv6. As more services become available natively over IPv6, the need for translation decreases. Application developers increasingly build IPv6 native applications, particularly for mobile platforms where IPv6-only connectivity is becoming common. The gradual retirement of legacy IPv4-only services will reduce translation requirements over time. However, this transition will span decades rather than years, with some IPv4 dependencies persisting far into the future. Evolution of the technology itself continues with performance optimizations, improved discovery mechanisms, and better integration with emerging protocols like QUIC, which already includes native support for connection migration across address changes. Hardware acceleration for translation functions improves throughput and reduces latency. Software-defined networking approaches enable more flexible PLAT deployment models, including distributed translation across edge computing infrastructure. The fundamental concepts behind 464x CLAT, particularly the combination of stateless client-side operation with stateful network-side functionality, may influence future protocol transition mechanisms beyond the IPv4-IPv6 context. As the Internet continues to evolve, similar hybrid approaches may prove valuable for enabling gradual transitions between other protocol generations while maintaining backward compatibility and operational efficiency. Thank you for your attendance. Please consider subscribing to the channel.